Let's go. So here is the picture that I keep in mind when I'm thinking about this linearization stuff. You can use a lot of words to talk about this. This picture is describing linearization or a tangent line approximation or error propagation, right? It's all kind of the same thing. And so here's what I really want to point out. And I'm also kind of going along with what's happening on this condor question that some of you have been asking about, which I don't happen to have. Oh, I do happen to have. So just to share with everybody for a moment, this is part of where this is coming from. Looking at this problem 2 here. We're not going to do this problem, but I'm going to reference it a bit. I'm sorry, what the heck is going on with my computer? Sorry. Am I sharing the right screen? Let me double check. Yeah. So anyway, the whole idea here is that you can approximate a function near a real number a using a linear approximation of f around a. And that is the linear approximation. And then they kind of ask you all these questions, which I'm going to talk about. So like, what's delta y approximately equal to? Okay. So here's the picture. Here's my function, f of x. I haven't written f of x because we're also kind of using x as a point on the x-axis. It's not too big a deal. And the idea is we are trying to approximate this f of x by not actually calculating it. And so what we're going to do is we're going to instead use the fact that this tangent line at this point A, and typically, although not always in your homework problems, A should be a place where it's easier to evaluate the function. Although there's definitely some fifth root problems where they're having you plug in 15, and that is not really true there. So at this point there, f of A should be easy to calculate. F of x, not so easy to calculate. So one idea is that you can use the equation of this line, which is just this y value, plus f prime of a times x minus a. And where is this coming from? Well, it's really coming from the fact that we know how to find the equation of a tangent line. I know that y minus the y value equals the slope times x minus the x value. But in this particular case, right, the slope is f prime of a, and the y value is f of a. And then we solve for y. So we write it as y, or L of x, equal to f of a plus the slope f prime of a times x minus a. So that's where the equation of this line is coming from. Then this handout kind of asks you to do some weird things. They want you to start with, I think they want you to start with f of a plus delta x minus f of a. So I'm actually looking at f of a plus delta x. So f of a plus delta x, right? That's where you're trying to figure out, I've called this distance here delta x. So a plus delta x is just this part right here. So I'm really just trying to find that. So f of a plus delta x is f of a. So right, so this part here, that's f of a, plus whatever this part is here, which is delta y, or delta f, sometimes people call it. Let me see one thing. I'm kind of covering up the chat. Sometimes I cover up the chat with things that people are writing in the chat, and I don't see what anyone's writing. Right. All right. So I've got my f of a plus my delta y. But then here's kind of the key thing. We're not going to calculate delta y. We're going to approximate delta y. Delta y is approximated by what I usually call dy, the differential. But there's a lot of names for it. So here's delta y, the actual change from here to here in the function value. And here's dy, the approximate change. Dy, as I like to think of it, is actually, if you think about the slope of this line being the rise over the run, dy is just the rise. So the way I kind of write it over here is, dy dx, the derivative, is equal to f prime of a. But then I can solve for dy by multiplying, right? We treat it like a fraction. We can solve for dy is equal to f prime of a dx, or as I often will say in my head, this is the rise, and the rise is equal to the slope times the run, because rise over run equals slope. So the rise equals the slope times the run. Also, I should point out here, this is where we start talking about sensitivity. I've never heard this word, I've never heard this word in the mathematical context before until I saw this handout, but it makes sense. So sensitivity, when you talk about the function being sensitive, or what the sensitivity is, the larger this f prime of a is, the more sensitive the function is to errors in your x values or input values. So if you have a change here and the slope is large, it's going to result in a really big change over here. So the sensitivity is just the slope of the tangent line. And if it's large, it magnifies a small change in your input into a large change in your output. If it's small, it can actually compress. So sensitivity, if it's bigger, your function is more sensitive. If it's smaller, your function is less sensitive to changes in the input. And we've got this over here. So I replaced delta y with dy approximately. And then dy is just your f prime of a times dx. And then dx is the change in x. It's not an approximation. And the change in x is just this delta x, or what we often call as x minus a. So here's kind of a whole picture summing up this process. If I'm trying to find the function evaluated to x, I'm going to get approximately f of a plus f prime of a times x minus a. I will also point out in the question on the Condor handout, they specifically actually are asking you to figure out to approximate delta y. And so what I would say is delta y, the way they do it is they say that delta y is this minus this. So they say delta y is f of a plus delta x minus f of a. And then your job is to approximate this with this. So this is approximately f of a plus dy minus f of a. And then the f of a is canceled. And you get dy, and dy is f prime of a dx. So again, I would really like you all to know that the actual change in the function value is approximated by this differential dy. That's the approximate change in the function value. Okay. We can come back to this if you want, but I'm going to go to the other side because there's still more. But let me know if you have questions. So here's an example. It's a very basic example. Suppose our function is x cubed. And we measure x, the input, to be 4 with an error of 0.2. And I also wrote on the side here, that's a 5% error. How do you know it's a 5% error? Because the amount of error, dx, divided by the measurement, x, is 0.2 divided by 4, which is 0.05 or 5%. So you're talking about something that have a percentage error or a relative error. The relative error of something is just the amount of error divided by the total value. That's going to come back to be important in a second. So the question here, so if I measure x to be 4 with an error of 0.2, and so you could, if you wanted, right, you could envision that we're actually trying to find the volume of a cube, right? I didn't think about that earlier, but I happened to pick an example that works out perfectly. So right, I could be saying, if I know that the edge length of my cube is 4 inches, and there's an error of 0.2 inches, what is the approximate error in the measurement of the volume? So we could actually find the error in the measurement of the volume, right? The actual error would be the volume of the largest cube possible, right? 4.2 cubed minus 4 cubed, which would be exactly, I need to use a calculator to do 4.2 cubed. 4.2 cubed is 74.088 minus 4 cubed, which is 64. So we get 10.088. So that's the exact error, right? If we think the side length is 2, but the error is possibly 0.2. Okay, so now how are we going to approximate the error? Well, we're going to approximate the error literally doing the stuff we just did on the other side. The approximate error is the actual error is delta f. We approximate delta f with df, or you can call it delta y and dy. And df, that's just the approximate change in y. That's your rise. It's your slope times your run. Or it's the sensitivity times your error in x if you want. So the sensitivity, well, if you take the derivative, right, because we need the slope of the tangent line, the derivative is 3x squared. But then we actually have to plug in the point we're looking at. I'm not going to plug in 4.2. I'm going to plug in 4. Right? I'm picking the easy point to plug in. 3 times 4 squared is 3 times 16, which is 48. So here's what this is saying. Our sensitivity is 48. That means a small change, or our slope is also 48, right? That means a small change in x is going to get magnified by 48. So when I calculate this, df dx, that's my small change. That's going to be, that's my slope. That's 48. And my run, or my change in x, that's 0.2. And 48 times 0.2 is 9.6. So that's my approximate error. It's a pretty good, right? I mean, it's off by a little bit. It's off by 0.488. But that's a pretty good approximation of what the error is, or yeah, what the error is here. So that is my approximate error in f. Now, we should also mention the relative error, because I think the relative error is easy. So we could just calculate the relative error very straightforwardly by saying, well, it's the error in f, which is 9.6, divided by the actual value of f, right? The actual volume of the cube, when the length is, the side length is 4 inches. Well, the volume of the cube is 4 cubed, which is 64. And 9.6 divided by 64 is 0.15, or 15%. Now, I want to make an observation here, because it's something that happens a lot. If you were talking about, so if you're talking about measuring something that's kind of a one-dimensional thing, like length, and then asking how it affects a three-dimensional thing like volume, the kind of cool thing here is that the percent error actually gets multiplied by that power, 3. Right? 5% times 3 is 15%. And that's not a coincidence. That's something that actually happens for a reason. It's also true if I asked about surface area. And if I said the error in measuring the side length was 5%, and I asked you what's the error measuring the surface area, I know that it's going to be 10%, because the surface area is dimension 2 and the length is dimension 1. Kind of a neat little thing. You should still do the math, but it's an interesting thing to observe. We can all, and here's where I want to show you how the math is really working out. So instead of actually just finding the numbers for delta f and f and plugging them in and getting 0.15, which is 15%, let's actually calculate delta f more mathematically. So I wrote it down here, I'm going to write it again so you guys can see it. So again, delta f over f, I'm going to approximate by df over f. df is this, it's the derivative times dx. Okay, pay attention. So df is, I'm going to write out df is df dx times dx. And f is just the function f of x. So df dx, that's my derivative, that's 3x squared times dx. And my function f of x is x cubed. And now check this out. 2x squareds cancel. So 2x squareds, 2x's cancel. So x squared cancels, x squared cancels. I'm left with 3 over x. That's not how I write that. I mean, I could write it that way, but I want to write it really as 3 times dx over x. Okay, can some brave person tell me what dx over x is in this particular problem?
5%.
Exactly. Dx over x is 5%, right? 5% was the error in x, that's the change in x divided by x. So you can write this, I should probably call it as 0.05, but yeah, this is 3 times 0.05. And so exactly that 3 that we're multiplying by is multiplying the relative error. I'm reading 0.15. It's kind of cool. Let me show you the surface area thing just because I think I would like to kind of extend our understanding of this. So let me erase it here. Just to kind of to show you how this actually does work for other things, it would also work for the surface area. the surface area of a cube, well, there's 6 faces. Each face has an area of x squared. So the surface area is 6x squared. And I'm asking what the relative error is. So the relative error is approximately ds over s, right? The change in the thing divided by the thing. That's going to be, well, ds and ds dx, derivative here is 12x. So ds is going to be 12x times dx. And s, we know, is 6x squared. Check it out. I can cancel a 6 and cancel an x. I'm left with 2 times dx over x. It's 2 times 0.05, which is 0.1, or 10%. So if the edge length has an error of 5%, the surface area can have an error of at most 10%. Kind of neat. And if there was some 4-dimensional thing, it would have an error of 20%. Okay. Yeah. So are there questions about anything we've said here? Nope. All right, let's do a couple examples of Newton's method. So we have certainly used, what is it? The linearization to approximate things, right? Like I could, I think someone asked me a question about this and I kind of missed what they were asking before. I feel like someone said there were 2 methods of approximating things and I was like, let's hear up. So in fact, let's do both. So we can use, we want to approximate the square root of 7. First, we're going to use the linearization. So again, I'm going to say that my function is equal to the square root of x. And I have to, pick a value that's close to 7 that's easy to deal with. What should I be picking? That's close to 7 that's easy to take the square root of. Should I pick 4 or should I pick 9? So it's not 8, Ellen. If it was a cube root, I would definitely pick 8. This is the square root, and I don't know what the square root of 8 is not a very nice number. It's a fine number, but it's not an integer. I want to pick a equal to 9 here, because the square root of 9 is 3. But yes, you would totally be right if I was talking about a cube root. So then our derivative, f prime of x, is 1/2 x to the negative 1/2. And then I need f of a, which is the square root of 9, which is 3, and f prime of a, which is 1/2 times 9 to the negative 1/2, which is 1 over 2 times the square root of 9, which is 1/6. There's my slope of my tangent line, and my point is x is 9 and y is 3. So my equation, my linearization is, and so I feel like, so I'm always just writing it this way because that's the way I learned it, but I feel like, oh, sorry, I forgot to admit someone. Oh, I thought I clicked on it, but I guess I didn't. Well, come on, left hand. I can do it. Yeah. Maybe I can't. Maybe I need to put down the eraser. Use right hand. Very right hand. Okay. So I think your book, instead of like saying linearization, they're just like, okay, well, this is the approximation of f of x. So like f of x is approximately f of a plus f prime of a times x minus a. I would call this the linearization. Fine. So f of a is 3. F prime of a is 1/6. And x minus a is x minus 9. So f of x is approximately 3 plus 1/6 times x minus 9. Also, I do want to point out, you really don't want to simplify this. Like you can multiply the 1/6 through and add the 3 and the 1/6 times negative 9. We don't want to do that. Because the idea is that when we approximate whatever we're approximating, it's going to be easier to simplify this if we leave this as is. So I'm going to say that f of 7 is approximately 3 plus 1/6 times 7 minus 9. And that's going to be 3 plus 1/6 times negative 2 is negative 1/3. So So it's 3 minus 1/3. So here's an excellent example of why you don't want to write your answer as a decimal. Right, we can write this as a decimal. It's 2.66666, right? Nobody wants to write that down. So instead, this is one of the reasons why your book or your web work says to write your answer as a fraction. Because writing this as a fraction is much easier. It's 9/3 minus 1/3, which is 8/3. Okay. So 8/3 is the approximation that the linearization would give us, or the tangent line approximation, if you want to call it that. But now there's another way of doing it. So I'm probably going to run out of room here, but I'll at least draw the picture. So the idea is to approximate the square root of 7 using Newton's method, you have to think about, and it's not a hard question, I'm just trying to phrase it the right way. You have to think about a function where the square root of 7 would be the root or the 0 of that function. It's not hard. In fact, here's what we do. If you don't know what the function is right off the bat, just say, well, I know I want this. And then I'm going to rewrite it so that, well, I'm going to square both sides. And I'm going to subtract 7. So I'm going to call this my function. I guess I'm going to give it a different name since I already used f of x over here. So I'm going to call this g of x. And I'm going to use Newton's method to approximate the root, or 0, whatever you want to call it, of g of x equal to x squared minus 7. So I want to point out, very kind of different in the beginning, right? I mean, here you're using the function square root of x, here you're using the function x squared minus 7. So they really are a different process. They are still both methods of approximation, they're different. So you really should memorize I should say, if you have to use Newton's method, you probably should memorize the formula. I have not memorized it because I don't use it all that much. But here's the idea. So x squared minus 7 is a parabola. It looks vaguely like this. And I'm trying to figure out what that point is right there. So I'm going to make a guess. So we have to first guess. And sometimes they'll tell you what your guess is. Sometimes you just have to guess a guess. So I'm going to use my calculator real quick. So I really should say our guess should be one of two things. If we're trying to guess the square root of 7, we need to pick a number that's close to what we think the answer is. We can reasonably pick 2 or 3. I think I'm going to pick 3 because I think 3 is a little bit closer. Not that it really, really matters here. So here's the idea. Here's the graphical idea. In case, I don't know if your teacher said much about this, but here's the whole kind of gist. And I'm going to redraw my graph so it's easier to draw the gist of what I'm trying to draw. Sorry, my graph is not exactly conducive to what I actually want to show you. Let's draw this again. Let's draw it a little bit wider. Okay, perfect. So right there, there's our square root of 7 that we're trying to approximate. So what we're going to do is we're going to pick a number that isn't actually the right answer. We're going to pick, say, 3. Now, we're not going to do this, draw this every time, but the whole, I have to be, no, right, okay, sorry, I was about to my brain always gets a little caught up with this one. So we're going to say, okay, well, if I plug in 3, I get, right, oh, sorry, I forgot. I'm like, what? Hold on, do something here. This function, right, this function is x squared minus 7. So we're guessing 3. So we plug in 3 to the function, and we get some value. We get 3 comma 3 squared minus 7 is 2. And then here's what we do. Through that point, we draw the tangent line. And the tangent line gives us our next guess. So if this is, we usually call this first guess x sub 0. Actually, I should double check if your book does it this way or the other way, just so it can be consistent. Let's see. No, they start with x1. Okay. So we call our first guess x sub 1. I guess that makes sense. It's our first guess. It's the 1 thing. And then whatever this point is here, that's our next guess, x sub 2. And then we repeat the process. We plug in whatever this is to the function. We get a y value out. And then we draw the tangent line there to get the next guess. So you can probably, I don't know. I feel like I'm going to try and draw this next one. It's going to look super messy. But the point is, right, you go up here, draw the tangent line. And at least in this example, every time you do that, you're getting closer and closer to actually the 0, which is root 7. So here's how the process works itself out. I'm plugging in 3, or I'm going to call it x1 for the moment. So I'm going to find f of x1. I guess I should say, I'm trying to figure out how to get to x2. So to get to x2, I need to find the equation of this tangent line. We have talked a lot about finding equations of tangent lines. Right, so the equation of the tangent line, let's do it that way. So the tangent line, well, we need a point and a slope. The point, instead of calling it 3, 2, I'm going to call it x1, comma f of x1. And the slope is the derivative through that point, which is f prime of x1. So that's going to end up giving me the tangent line equation that y minus y1 is equal to the slope times, sorry, I made a tiny mistake. It's not a huge mistake. It's a little mistake. So yeah, let me back up just a little bit. Sorry, there's a smarter way of doing this that I was kind of forgetting about. Apologies. So instead of finding the equation of the tangent line, we're just going to find the slope. So the slope is either the derivative, but it's also equal to the slope through those 2 points. So those points are, right, over here the point is x1 comma f of x1, and over here the point is x2 comma 0. And so the slope between those 2 points is the difference in the y's over the difference in the x's. And now we can solve for x2. So multiply both sides by this. x1 minus x2 equals f of x, times f prime of x1, the 1, equals f of x1 minus 0. And then we can divide both sides by f prime of x1. So x1 minus x2 equals f of x1 divided by f prime of x1. And then add x2 and subtract this to get that x2 equals x1 minus f of x1 over f prime of x1. So that's how we find our next point. We do this iterative process where we say, okay, well, I'm going to take my guess of 3, and then I'm going to subtract f of 3 over f prime of 3. Again, I should really point out, so you can kind of, it's totally, so again, I'm kind of totally using the differential here, right? I'm taking 3, and I'm trying to subtract this amount, which is just the run. And the run is exactly the rise divided by the slope, right? Rise over run equals slope. So rise over slope equals the run. That's kind of neat. From here, you're trying to get to here by just figuring out what the run of the slope of that tangent line is. Okay, that's not nothing. But really, so you could probably ignore all of this if you wanted to and just memorize the formula. So to answer the question here, my x1 is 3. I probably should write down the derivative, right? My f prime of x is 2x. So then my x2 is going to be 3 minus f of x1 over f prime of x1. So it's going to be 3 minus f of 3 over f prime of 3, which is going to be 3 minus, let's see, f of 3 is 9 minus 7, which is 2. F prime of 3 is 2 times 3, which is 6. Which is 3 minus 1/3, which is the same answer we got before. That's kind of a coincidence, maybe a little bit. Maybe not a huge coincidence, actually. So that's going to be 26 thirds. Sorry, I'm really not doing the math right there. That's not 26 thirds, that's 8 thirds. But the difference here is that we can keep going. And we can get a better approximation if we then do it again. So x sub 3 would be, so you take now your previous one and use that. So instead of 3 minus f of 3 over f prime of 3, it's going to be 8 thirds minus f of 8 thirds over f prime of 8 thirds. Now the problem with Newton's method is you get to a point where you probably have to start pulling out a calculator to calculate things. And at that point, you're like, well, why don't I just use a calculator to approximate the square root of 7? But this is the idea. So we could probably calculate this. This is going to be 8 thirds minus f of 8 thirds is 8 thirds squared, which is 64 ninths, minus 7, which is 63 ninths, all over 2 times 8 thirds, which is 16 thirds. And so this ends up being something, I don't know. Right, this is just where the numbers get gross. So you get 8 thirds minus 1/9 divided by this is times this. Sure, cancel there. So you get 8 thirds minus 1 over 3 times 16. Multiply this by 16 over 16. And you get 16 times 8, which is 128 over 16 times, minus 1 over 48. Okay, so we get 127 over 48. Awesome. And you can keep doing this, right? Then you could, right, but it just gets really, really gross. So usually after 1 or 2 or maybe 3 iterations, we're kind of like, okay, we're done. Usually if you're doing a Newton's method problem like this, typically someone will tell you when to stop. Like in the example, there's only like 2, I guess there's, oh, okay, sure. So there's a couple in the textbook. So one of the ones in the textbook says the following. Says, use Newton's method with the specified initial approximation to find the third approximation. Okay, so here's one example. Let's do this one. F of x equal to x cubed plus 2x minus 4. And we want to approximate, so we're, again, Newton's method, we're trying to find the root. So we're going to approximate the root with x1 equal to 1. Is that actually a root? No. If you plug in 1, you get 1 plus 2 minus 4, which is not 1, or which is not 0, it's negative 1. So then we just literally throw things into the formula. So, right, our formula, the way the formula is more generally written is that the next value, x of n plus 1, is equal to the previous value minus the function at that value over the derivative at that value. That's the actual Newton's method formula. Your book might have written it slightly differently, but that is the idea nonetheless. Now I feel like I need to look and see. Nope, they wrote it exactly like that. So then we plug in 1 to get to. So x sub 2 is going to be x sub 1 minus f of x sub 1 over f prime of x sub 1. In this case, that's going to be 1 minus f of 1 is 1 plus 2 minus 4, which is negative 1. F prime of 1, I guess we should find the derivative. The derivative is 3x squared plus 2. So f prime of 1 is 3 plus 2, which is 5. So 1 minus negative 1/5 is 6/5. And then we find the third iteration by plugging that into the next one. So x of 3 is going to be 6/5 minus f of 6/5 over f prime of 6/5. All right, this is where things get gross, because you're going to have to do 6/5 cubed. But we get 6/5 minus 6/5 cubed, blah. That's 216 over 125 minus 2 times, sorry, plus 2 times 6/5 minus 4 all over 3 times 6/5 squared plus 2. And I'm not going to simplify that. You could simplify that on your own, but like the point is not doing that. Right? It's kind of like, the other type of Newton's method question, which is by far more annoying, is something like the next question, something like problem 23, which is use Newton's method to find all roots of the equation, correct the 6 decimal places. We might not finish this problem, but let me see if any of these are not terrible. Nope, they're all terrible. That one's not super duper terrible. Yeah, they're all pretty gross though. Well, I'm going to start this one, and then I'm going to tell you how it goes. And then we're going to move on to Taylor and polynomials, and then finally we'll talk about some graphics. Okay, so here is the problem. We want to find solutions to x to the 4th equal to 1 plus x to 6 decimal places. Okay, so whenever you're trying to solve an equation like this, or to approximate solutions to an equation like this, you really want it to be equal to 0, right? Kind of like with, oh, brain, where'd you go? There was something else I literally just thought of, which we also do that. Oh, for the intermediate value theorem, right? When we were doing intermediate value theorem problems, and we wanted to show that there was a solution, not that we were finding it, we would always bring everything to one side, so we were actually trying to show where the thing was equal to 0, because it was just easier to do it that way. So we want to rewrite this as x to the 4th minus x minus 1 equals to 0. I'm going to call this x. And then f prime of x is 4x cubed minus 1. Okay, so here's the thing. They didn't tell us where to start. So we have to guess. My guess would probably be either 0 or 1. I feel like 0 is a dumb guess because I don't think it actually gets you anywhere. Right? If you plug in 0, it's a -1. If you plug in 1, it's +1. So it seems like, well, I know my answer is somewhere between 0 and 1, so that seems like a good place to start. Let's start at 1. So x1 is 1. x2 is x1 minus f of 1. F of 1 is 1 minus 1 minus 1, which is -1, right? Now I'm like, is it 1? Yeah, it's -1. Over f prime of 1, which is going to be 4 minus 1, which is 3. So I'm a little concerned here, and here's why. I know there's an answer between 0 and 1, right? Because of the intermediate value theorem, right? F of 0 is -1. F of 1, I made a mistake. That's Sorry, I made a mistake previously. There isn't a solution between 0 and 1. I made an error. F of 0 is 0 minus 0 minus 1, which is -1. And f of 1 is 1 minus 1 minus 1, which is also -1. So I made an error. I made a mistake earlier saying there's a solution to that. There's probably a solution between 1 and 2. Because f of 2 is 16 minus 2 minus 1, which is definitely positive, right? It's 13. Okay, so here's why I was concerned. Let me just spell this out, just so you guys can hear my thought process. I thought there was a solution between 0 and 1. I plugged in 1, and then my next iteration got further away from where I thought my answer was. That's why I was concerned. But now I'm not concerned because I know my answer is actually between 1 and 2. So that's actually okay. But if I was supposed to get an answer between 0 and 1, this would be bad news that I went from 1 and I went further away from it. So that's what's happening. That's why I thought that. Okay, so here's the thing. I'm not going to finish this problem. Let me do the next one and then talk about what you would have to do. So x of 3 is going to be this, right? It's going to be 4/3 minus f of 4/3, blah, okay. So f of 4/3 is 4/3 to the 4th minus 4/3 minus 1 over 4 times 4/3 to the 3rd minus 1. Terrible, we don't want to do that. So here's the idea, and it's really not, this is where you definitely should use a calculator. Because to approximate the root of this to 6 decimal places, you have to keep plugging this in and doing this iterative process until your answers don't change to the 6 decimal place. Now, yeah, it's not fun. There is a way you can make this a little bit easier on yourself, I think. Let me show you how I would try to make my life easier with this problem on this. So, yeah. Let me show you. I think this will work. So I want my function to be, so I want to be able to put in an x and get out that mess over there. So I actually want my function to be f of x equal to x minus my f prime, sorry, my f of x, which is x to the 4th. Minus x minus 1 over f of x, which was, sorry, f prime of x, which is 4x cubed minus 1. Okay, so then what I really want to be able to do is plug in values here. And of course, I don't really actually know how to do that because maybe I can make a table. Yeah, let's do a table where I get x and y1. Can I call this f of x? Probably not. I'm sure there's a way to do this. Let me call this y1 maybe, if I'm smart. What I want to do is like put the number in here and get the number out there. No, of course not. I guess I could do this. What's my problem there? Too many variables. Try defining x. Fine, okay. They're like, no. Well, anyway, the point I was trying to make is that I've definitely done this on the graphing calculator before, where, yeah, okay, you don't like me, that's fine. No, that's not what I want to do. Yeah. Sweet. That's what I wanted. So here's what I can do. I want to start with 1. Yeah. So there's my 1. And then I would really like to know, so if I plug in that, I'm thinking this will work. Let's find out. Yeah, cool. And then I can take this number, maybe. Can I not copy you? Give me the number. No. But that's kind of the idea I'm thinking of, is you could just, wow, that's not, ooh, you're bonkers. Is that you could take, right, because it's an iterative process. So I plug in 1, I get 4/3. I plug in 4/3, oh my gosh, holy smokes. Go away. I just wanted this to go away. Oh my God. You are terrible. Why can't you go away like I want you to? There. But I could plug in that number right there, like 1.23588079. And then I get the next number. So I can plug that one in and get 1.221059. Did you plug in the next one and get, right? And so I'm getting closer and closer to the actual answer. This is kind of fun. I'm not going to lie. I mean, fun, you know. And then, so, right, so then I plug in the next one, 1.2207441. And then look, looks like my answer is pretty good to 6 decimal places. I plugged in 1.2207441 and I got 1.2207441. Kind of cool. So let's look in the book to see if we're right, because it's always good to check your answers. So this is problem 23 from section whatever, section 3.8. Section 3.8. If I look at the answer, sorry, 1 second. Section 3.8, 23. Yeah, we're right on. It is 1.220744. Cool. So you could totally do this, right? So basically, I wrote out the formula for Newton's method, right? Where instead of writing x1 or whatever, I was just doing x minus the function over the derivative. And then I took my input, and then every time I put in input, I got my new output, and then I put that in for my next input. And I just kept doing that until I got to a place where the input and the output essentially matched. That's not terrible. Oh, sorry, there's someone chatting. I didn't see it. Stop sharing. What if you put answer? Oh, maybe that might work. That's a good. That might work as well, Emily. That's what I would do with a calculator. Desmos, I'm not as familiar with. But yeah, I've definitely used. Yeah, you could probably do that with a calculator as well. I don't have my favorite calculator is not working anymore, so this calculator I'm less good at using. But yeah, that would probably work as well. All right, so I think that's enough Newton's method. Let's do one example of a Taylor polynomial, and then we will go on. So I will also say these are all methods of estimating things. Yeah. So a Taylor polynomial. So let's find the Taylor polynomial of degree, I don't know, let's go degree 3 for, let's pick something not too insane. F of x equal to, sure, 6x to the 4th plus 3x cubed plus x squared plus 2x. All right. So here's what the Taylor polynomial is of any degree. The Taylor polynomial of degree 3 is literally a degree 3 polynomial that approximates this function. You also have to pick where it's centered. I'm going to say that it's centered. I'm going to pick an easy one first, centered at x equal to 0. All right, this is probably just the formula you want to memorize. Here's how it works. So the Taylor polynomial for a function f of x is the following. It's equal to f of a plus f prime of a times x minus a plus f double prime of a times x minus a squared over 2 plus f triple prime of a times x minus a squared over 3 factorial, which is 6. That's right that way. And so on and so on and so on, where a is the center. And x is just x. And I should also say, even though I didn't write it, each term you're dividing by the next biggest factorial. So really here you are dividing by 0 factorial. And here you're dividing by 1 factorial. Here you're dividing by 2 factorial, by 3 factorial, and so on and so forth. Where 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1. 1 factorial is 1. And 0 factorial is defined to be equal to 1. So any factorial, like when I say 20 factorial, it's a really big number. It just means 20 times 19 times 18 times 17 times 16, all the way down to times 5 times 4 times 3 times 2 times 1. So that's what a factorial is. So this is how you approximate a function. So, or I should say, this is one way of approximating a function with a polynomial. So if I want to approximate this, all right, it's going to be, I'm just going to write down what the function is. So f of 0 is going to be 1. F prime of 0, well, if I take the derivative, it's going to be, I should really write the derivative first. So f prime of x is going to be 24x cubed plus 9x squared plus 2x plus 2. And then f prime of 0 is just going to be 2. And then f double prime of x is going to be, let's see, the second derivative is going to be 72x squared plus 18x plus 2 again. So f double prime of 0 is going to be 2. And since I need a degree 3, I need to have all the way to the third derivative. So then, running out of room, sorry, the third derivative is equal to 144x plus 18. And so the third derivative at 0 is going to be just 18. Now I'm going to point out this answer is not going to be very exciting because I'm using a polynomial to approximate a polynomial at 0. So here's what our answer is going to be. Let's see, I have it from here. So we're going to get that f of x is approximately equal to, so it's going to be f of a, so f of 0, so 1, plus f prime of a, which is, or f prime of 0, which is 2 times x minus 0, plus f double prime of 0, which is 2, divided by 2 times x minus 0 squared, plus f double prime of 0, which is 18, divided by 3 factorial, which is 6, times x minus 0 cubed. But look, this is just 1 plus 2x plus x squared plus 3x cubed. I'm just missing that term. And the reason I'm missing that term is because I said I wanted a degree 3 polynomial. So the approximation of this function near x equals 0 with a third degree polynomial is just the same thing without the fourth degree term. Let me show you, because I think it is worth seeing what we're actually looking at here. Let me share again. Also, yeah, I was happy that I was able to like click on this and actually just make a table come out. I don't even remember how I did it now, but oh yeah, that's what I did. Okay, good, cool. Anyway, let's get rid of this. I want to graph these two things. So my functions are f of x is, let's just call it f of x, is 6x to the fourth plus 3x cubed plus x squared plus 2x plus 1. And the Taylor polynomial, oops, not that. And the Taylor polynomial is just, in this particular case, just all of that. And so if we look at this here, we can see that, okay, near x equal to 0, yeah, that purple function is a really good approximation of that green function. But if we go too far away from 0, oh yeah, it stops being a very good approximation. So that's kind of the general truth about Taylor polynomials. Near the center where you're actually approximating things at, it's a good approximation. But if you move too far away from that center point, it is not a good approximation. Oh, excuse me. 0 is often the nicest place to approximate things at, but you can certainly pick kind of any center. So let's do one more example. Okay, let's say I want to approximate f of x equal to the square root of x centered at a equal to 1 with a, we'll actually talk about, let's say a first second and a third degree Taylor polynomial. Okay, ow, son of a gun. Ooh, Ooh, okay, that felt not good. All right. We're going to make an observation as well. So let's do the first degree Taylor polynomial. So I'm going to call that T1 for first degree Taylor polynomial. So that's going to be, so here's the interesting thing about Taylor polynomials. If I have a degree, it's not the number of terms, it's the last power. So my first term doesn't have any power of x. So actually I need to go to my second term to get a first degree Taylor polynomial. This is going to be f of 1 plus f prime of 1 times x minus 1. And I want to make sure that everybody sees that the first degree Taylor polynomial is literally the same thing as the linearization, right? It's f of a plus f prime of a times x minus a. That is the tangent line equation for the function at that point. So first degree Taylor polynomial is the literal same thing as the linearization. Good to know. But then we can find it, right? So that's going to be, I should also maybe find some derivatives over here. So my function is x to the 1/2. My derivative is 1/2 x to the negative 1/2. Luckily, we're plugging in 1, and 1 to any power is still 1. So f of 1 is going to be 1, and f prime of 1 is going to be 1/2 times 1 to any power is 1. So it's going to be 1/2 times x minus 1. So there's the first degree Taylor polynomial approximation of the square root of x at a equals 1. Let's find the second degree one. So here's the thing. The second degree one is going to be the first degree one plus the next term, right? It's going to be f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 over 2 factorial times x minus 1 squared. So I really just need to find the next piece. So the second derivative here, f double prime of x, is going to be, well, again, the power comes down, and I get 1/2 times negative 1/2 x to the negative 3/2. So f double prime of 1 is going to be 1/2 times negative 1/2 times 1, which is negative 1/4. This is going to be 1 plus 1/2 times x minus 1 plus f double prime, we just said was negative 1/4. So it's going to be negative 1/4 divided by 2, which is negative 1/8. That's our second degree Taylor polynomial. And then for our third degree Taylor polynomial, it's going to be, so here, I'm going to write that this way. The third degree one is going to be, it's going to be all of this, which I'm going to write it like this for a moment. Right? If the third degree is the second degree plus whatever that last term is, which is going to be f triple prime of x, f triple prime of 1 divided by 3 factorial, which is 3 times 2 times 1, which is 6, times x minus 1 cubed. So if we look at that, so I need f triple prime of x. So the negative 3/2 comes down, so I get 1/2 times negative 1/2 times negative 3/2 x to the negative 5/2. Which when I plug in 1 gives me 1/2 times negative 1/2 times negative 3/2 times 1. So that's going to be 3/8. So that's going to be a 3/8. And 3/8 divided by 6 is going to be 1/16. 3/8 divided by 6, yeah, it's 1/16. So this ends up being, I'm going to have to give myself some room up here. So this ends up being all of this. So it's 1 plus 1/2 times x minus 1 minus 1/8 times x minus 1 squared plus 1/16, that's all this, times x minus 1 cubed. So that is your third degree Taylor polynomial for the square root of x. And again, I feel compelled to just show you guys what's happening here. So if we look at the graphs of these things, right? So the function we're approximating is just the square root of x. Let's make this a little bit bigger. And so first we're just, and again, we're doing it at x equal to 1. Well, I should maybe zoom out just a little bit. Yeah, that's better. Okay. So, right, first degree Taylor polynomial, that's going to be, well, we found it was, and I'm not simplifying this, right? You can, I don't think that's the point though. Right, just the tangent line. And then here's our second degree Taylor polynomial. So the nice thing here is I can definitely do some copying and pasting. Let's grab all of this. And let's add on the next term, which is actually a negative 1/8 x minus 1. So you can see, hopefully, that this blue function is definitely a better approximation of the black function for a good period, right? I mean, definitely better than, it's certainly, the blue one is closer to the black one, sorry, is closer than the red one is to the black one over here. And over here, it's certainly closer for a bit, although as we go out, as I need to zoom out, not just try and, right? As you go out, right, it definitely gets further away. So close to 1, yeah, that blue one's a good approximation. And then if we do the third degree Taylor polynomial, oops, I'm going to be able to capitalize like that. If we add on the last term, which is 1/16 x minus 1 cubed, that's right. The green one is even better than the blue one in here, right? The green one's closer to the black function. And certainly over here, it's definitely closer to the blue function, and it's closer for quite a while. So you can keep doing this literally forever and get closer and closer and closer approximations of the square root of x. Now, you might ask, why the heck would you do that? And some of the reasons are polynomials are really easy to deal with. So if you're trying to get a good idea of what a function is doing, maybe you want it to be really differentiable or easy to manipulate or something like that, it is often not a bad idea to approximate a function with a polynomial, because polynomials have all the nice properties that you really want for a function. Okay, that's all I really have to say about Taylor polynomials. Let us move on to chapter 4 and start talking about maxes and mins a little bit and all those good things in there. Let me look one real quick at my notes here. Let's see, that, sure. Right, okay. So, there's a theorem called the extreme value theorem that says a continuous function on a closed interval has to attain or achieve its absolute maximum and absolute minimum. And there's some pictures we can kind of draw to indicate this. For example, if I've got some function on some closed interval from, say, A to B, maybe it looks like this. And so let's see, it definitely has a maximum there, right? That's the absolute maximum. And it looks like it's the lowest value is right there, absolute minimum. But maybe it doesn't look like that. Maybe it looks like this. Maybe it looks like, I don't know, here's A and here's B, and maybe it does this kind of deal. So that or maybe, in fact, let me make it a little bit more interesting. Maybe it does this. Yeah, that's better. So in this particular problem, and you can imagine the function continuing on this way and that way or whatever, right? We don't really care what's happening outside of the interval. In this function, the absolute maximum is right there at the end, and the absolute minimum is right there at the beginning. And although we could draw a lot more pictures, there's kind of two competing ideas about where the absolute maximum can be. For a continuous function, closed interval, the absolute maximum, sorry, I should really say the absolute extrema, meaning max or min, occur at either a critical value, a critical value is just where the function has a derivative that's 0 or undefined. So where the derivative is equal to 0 or undefined, like right here, the derivative is 0, right? The tangent line is horizontal, slope is 0, and right here, and right here, and right here. All those places are where the derivative is 0. Clearly, though, we can see that the absolute extrema don't always occur where the derivative is 0 at a critical value. They can also occur at either or an endpoint. So that's where you can have an absolute maximum, or some people call it a global maximum or minimum. And there's a method for finding them called the, I think your book calls it the closed interval method, or the closed interval test. The idea basically is to identify all the points that could be either critical values or endpoints, and then literally just plug them into the original function to see which is the biggest and which is the smallest. Let me draw one more picture just to point out that you could have something like this. You could have, sure, a function that does this. We'll actually look at this example. I'll make it. But here's the function, definitely continuous on the interval from A to B, and it has a minimum right there where the derivative is undefined, right? You've got a cusp, also known as a pointy point, as I like to call it, and the maximum is right there. So yeah, you can have an absolute extrema at an endpoint, at a place where the derivative is 0, or at a place where the derivative is undefined. All those are valid places for the absolute extrema or global extrema to occur at. Let's look at a couple examples. I should also mention, just because we're looking at these points right here, this point, this point, this point, this point, and this point, those are also qualifying as local extrema or relative extrema. This point here is a local maximum. It's bigger than all the things next to it. This point here is a local minimum. It's smaller than all the things next to it. This point here is also a local maximum. It's not a global maximum. That's okay. This point here is also a local minimum. It's smaller than all the things next to it. This point here is also a local or relative minimum. It's smaller than all the things next to it. These endpoints are not local extrema in any way, shape, or form, because they're not less than or equal to all the things or greater than or equal to all the things next to it, because it's not defined on one side. So we don't talk about endpoints being relative or local extrema. Okay, well, let's do a couple of examples. Let's find the global max and min for f of x equal to x cubed minus 6x squared on the interval from -1 to 7. So our job is to do like 3 things. Find the critical values, find where the derivative is 0, find the endpoints, literally they're given to us, and then plug them all into the original function to see what's the largest and what's the smallest. So critical values, take the derivative, which is 3x squared minus 12x, so it's equal to 0. Factor. Take 3x and x minus 4 equal to 0. So my critical values are x equal to 0 and x equal to 4. So let's see. Now I'm going to plug them all into the original. So I'm going to plug in 0 and 4 and negative 1 and 7. Sorry, negative 1. And also, to make my life easier, so, well, I mean, okay, 0 is fine. F of 0 is just 0 minus 0, no big deal. You can probably even do negative 1 without too much trouble, right? F of negative 1 is negative 1 cubed, which is negative 1, minus 6 times negative 1 squared is minus 6, and negative 1 minus 6 is negative 7. But then things get maybe trickier than I want to think about when I plug in 4. 4 cubed, okay, that's 64. 64 squared, it's easier if we factor, right? If you factor this f of x, if you factor out the x squared, and write it as x squared times x minus 6, it's generally way easier to plug stuff into that. 4 squared is 16. 4 minus 6 is negative 2. 16 times negative 2 is negative 32. It's also way easier with 7. 7 cubed is 343. 6 times 7 squared is I. But if you do it here, 7 squared is 49. 7 minus 6 is 1. 49 times 1 is 49. It's really super easy. So, piece of advice, if you're plugging things back into the original function, it really does pay to factor the original function if you can. So, what's the global maximum?
7.
So that's not necessarily a wrong answer, but it depends on how the question is asked. So if I said, what's the global maximum? The global maximum is the y value. You could say the global maximum occurs at x equals to 7. In the same way, the global minimum is negative 32, and it occurs, or is at, x equal to 4. So when someone asks you where a relative or a global extrema is, it's at the x value and there's a value of the y value. Let's do another example.
Hey, sorry, on the other one, I was just wondering, like, how did you know that? I keep forgetting, like, how do you know, like, so at the 3x, how do you know that x is a 0?
So one more time? Oh. Well, really, I'm not.
Yeah, like.
I mean, you could set 3x equal to 0 and then divide both sides by 3. But 0 divided by 3.
Okay.
Really,
yeah, you're just trying to find like anything to get it the whole thing equal to 0.
And really, I'm not even paying attention to the 3 there. I'm really thinking of it as 3 times x minus 4.
Okay.
Let me grab another example here just because I want something specific to come up. Not you, maybe you. Sorry, I thought I had an example ready to go. Let's look at, sure, we'll do this one. Let's look at f of x equal to x to the 1/3 on the interval from -1 to 8. So let's find the critical values. Derivative is 1/3 x to the -2/3. All right, this is kind of a trick question I'm about to ask you guys. Does anything make this equal to 0? Well, the answer is no. right? If you plug in 0 here, you don't get 0. You get 0 to the negative 2/3, which is undefined. Fortunately, that's still something we want, right? So no, it's never equal to 0, but it is undefined. 1/3 to the negative 2/3 undefined. Yeah, for sure, because this is really, you can rewrite this as 1/3 to the 2/3. And then I think it's a little more clear that if x is 0, division by 0 means it's undefined. The thing I will say, though, is if you accidentally make the mistake of thinking that something makes it 0 when it really makes it undefined, you still probably got yourself a critical value anyway, so it's not too much of a thing to worry about. So, yeah. So the function, the derivative is undefined there, but the function still is defined. That's not the function I actually wanted to do. Oh well. Sorry, so the function I actually want, so I'm going to fix this problem because I have enough time. Just because I want to show you guys something different. I really want to do x to the 2/3, which should have a derivative that is 2/3 x to the negative 1/3. Sorry. And this is 2/3 to the 1/3. It's still undefined at the same point, but it has a different looking graph, and so I wanted to kind of point that out. So let's see what's the biggest and what's small. So I've got this point, and then I've got my endpoints. I should also mention, although I didn't have any examples that showed this, the critical values you get have to be in the interval you're working in. If you get critical values outside of that interval, we don't count them. We don't use them. So make sure you're only checking values that end up between those endpoints. So now we're going to look at all of these. F of -1, f of 0, f of 8. F of -1 is -1 to the 2/3 power, which is +1. So it's -1 squared, which is 1, and then the cube root of 1, which is 1. F of 0 is easy. 0 to a positive power is 0. And then finally, f of 8, 8 to the 2/3 is 8 to the 1/3 squared, which is 2 squared, which is 4. So the maximum value is 4. It occurs at 8. The minimum value is 0. It occurs at 0. And here's what this looks like. So we got -1, 1, and we've got 8, 4, and it looks like this. So the derivative is undefined at 0, but you still have a minimum at 0. You have a maximum over there at 8. All right, sorry we didn't get to the mean value theorem. We'll definitely talk about that next week after Thanksgiving. If you guys have questions, you're still welcome to email me over the break. You are welcome to post a discussion in Canvas, which a lot of you have asked me really good questions in your reflections. And I was thinking those would be great questions to ask in a discussion so other students could see what's happening. So yeah, that's an option. Emailing me is an option. And the last thing I'll say, just real quick, is that even though we didn't talk about the mean value theorem, what I will say about the mean value theorem is that the idea of the mean value theorem is that if you have a function that's continuous and differentiable, then somewhere your average rate, so your instantaneous rate of change has to equal your average rate of change. An example I use is, let's say that you drove a mile in a minute. Your average speed is 1 mile per minute, which is 60 miles per hour. So the question is, did you actually ever go 60 miles an hour? Could you have always been less than 60 miles an hour? No. If you were always less, your average would not be 60. Could you always be more than 60? No. Your average can't be more than, if you're always more than 60, your average won't be 60. So since your average is 60, you had to at some point go from below 60 to above 60, or be always 60. But so the whole real big idea with the mean value theorem is that if you have something that isn't weird and jerky, it's continuous and differentiable, if you know the average rate of change for that function, somewhere in between the first point and the last point, the instantaneous rate of change, or the derivative, has to equal the average rate of change. That is the whole big idea with the mean value theorem. I know